Assalamualaikum warahmatullahi wabarakatuh. My name is Izzany binti Mohd Idris from Section 2 Group 1 with matric number CE 200-231, and I will present for calculation. So the specification of 6 order band pass activator for our group are given as mid gain. A is 100. Then the lower cut off is 200 Hz, and for high cut off the value is 1000 Hz. So from here we can get central frequency FC, which is using this formula, so we get 447.21 Hz. Then for bandwidth, by using this formula we get 800 Hz. Next, for quality factor Q, we get 0.56. Next, high pass filter. They have 3 nodes with X, Y and Z. According to amplifier gain, we have this formula. So at Y naught, this is the formula that we use, and substitute J omega equal to S. So from this formula, substitute J omega to S, which we get this formula. Then Z naught, we get this formula. So from here, let R1, R2, R3, R4, R5 and R6 equal to R, and C1, C2, C3, C4, C5 and C6 equal to C. Therefore, the overall gain will be like this. Next, for the cut-off frequency, we know that the formula is FL equal 1 over 2 pi RC. So we assume that value R is equal 10 kilo. So therefore, C is equal to 79.577 nanofarad. So hence, we can say that R1 equal to R2 equal to R3 equal to R4 equal to R5 equal to R6 is equal to 10 k ohm, and C1 equal to C2 equal to C3 equal to C4 equal to C5 equal to 66 is equal 79.577 nanofarad. Next, if you can see here is a Butterworth polynomial table that we use to find the ratio for RF over RA. Then we proceed with using the formula of gain to find the value of RF1, RF2 and RF3. So this is the formula that we use by letting RA1, RA2, RA3 and R1 is equal to 10 k ohm. So the RF1 is equal to 14820 ohm. RF2 is equal to 5860 ohm and RF3 is equal to 680 ohm. Therefore, we can say that RA1, RA2, RA3 and R1 is equal to 10 k ohm. After we done the high pass filter with the calculation, now we have to calculate the low pass filter. According to this circuit, which is the 2 order, here are 3 nodes which is X, Y and Z in first 3 partial filter. At X naught, this is a formula. For amplifier gain is in the formula. At Y naught, this is a formula, and at Z naught, here is the formula. Next, we let the R7 equal to R8, R9, R10, R11 and R12 is equal to R, and C7, C8, C9, C10, C11 and C12 will be equal to C. So this is overall gain will be in this formula. Cut off frequency FH is equal 1 over 2 pi RC, and we assume a value for resistor R is equal 10 k ohm, so will be equal to 15.92 nanofarad. This is the formula that we use by letting RF4, RF5, RF6 and R1 is equal to 10 k ohm. So the RF4 is equal to 14820 ohm, RF5 is equal to 5860 ohm and RF6 is equal to 680 ohm. Therefore, we can say that RF4, RF5, RF6 and R1 is equal to 10 k ohm. To achieve the mid gain A, a non-inverting is inserted into the circuit. By using the formula, the gain for our circuit is calculated based on formula. Then we proceed to calculate the R13 and R14 of the non-inverting amplifier using the gain based on the formula. And for R14, we assume that is equal to 10 k ohm. We get R13 is equal to 108.93 k ohm. So that's all from me. For now, I will pass to my next member for the next explanation. Thank you.
Hi, my name is Sin Yee. So I will explain for the simulation part. So since our project require us to do a 6-order bandpass filter, so it's actually a cascade circuit of 3-second order of high pass filter and 3-second order of low pass filter. So the value of resistor and capacitor is as shown in the calculation just now. That's all for my part. Thank you.
Hi, my name is Phoebe and I'll present about the result. So after running the simulation, this is a graph that we'll get, and then we'll extract the values that we need from this graph. Analysis. For this assignment, we are asked to design a 6-order bandpass active filter. We use 3 low-pass filter and 3 high-pass filter for the design. The graph shown in the result after running the simulation is known as the bandpass graph. After extracting the information we obtained from the simulation, we compare the data with our manual calculated result with the parameter that given by our lecturer. For the low cut frequency, we get the result very near to the given value, which is 200 Hz. And from the simulation, we get is 196.4826 Hz. And then for the high cut frequency, the result we obtain is also very near to the given value, 1000 Hz. And the simulation is 998.2209 Hz. And then from these two, we will get the value for center frequency, which we multiply the low cut frequency and high cut frequency and then square it. So the calculation is 447.21 Hz, and from the simulation we get is 442.8691 Hz. And from the low cut frequency and high cut frequency, we can calculate the bandwidth by subtracting high cut frequency with the low cut frequency. So from the calculation, we get 800, and then from the simulation, we'll get 801.7383. For the conclusion, throughout this assignment, we successfully designed and simulated a 6-order bandpass filter using OM with 3 low-pass filter and 3 high-pass filter, and also the parameters given by the lecturer. The estimated value of the low-pass frequency should be 200, high-pass frequency should be 1000 Hz, and from these two, the bandwidth should be 800. We carried out the simulation using NI multisim by constructing the circuit using the components available such as OM, resistors, and capacitors. After the running of the simulation, we successfully obtained the result with a slightly difference in terms of the values of low pass frequency, high pass frequency, and later the calculated bandwidth. This is due to the real-time simulation might be disturbed by some external causes. NI multisim has given us the advantage of building a circuit model faster compared into real life. So active filters are important as they are mostly used in communication system to improve the message signals from modulated signal, suppress external noises, and isolate a communication signal from other channels. OM are always used as it is easily create many types of active filters that can carry out different functions according to the needs. That's all from us. Thank you.